This is a video lesson on teaching you how to balance chemical reactions. In a previous chapter earlier in the year, we talked about chemical reactions. We talked about the basics of a chemical reaction, the reactants, the products, the reaction arrow. But it struck a lot of people right away that those chemical reactions that we were looking at didn't look quite right. Here's an example of one that we did in class. If you took N2 and reacted it with H2 and you got NH3, what jumped out at people right away is that I have two nitrogens on the left, but only one on the right of the arrow. Furthermore, I have two hydrogens on the left and three on the right. It appears as though I created some atoms and lost some atoms, and in fact, that's impossible. There's something called the law of conservation of matter. The law of conservation of matter states that matter, in this case atoms, cannot be created or destroyed in a chemical reaction. And as the reaction is written, we are destroying one nitrogen while creating one hydrogen. Now, to remedy this problem, we can do something called balancing the reaction. And balancing the reaction, basically what your job is to do is to get the same number of atoms on both sides of the reaction arrow. And in order to do this, the one thing that we can't do is change the formulas of the chemical reaction, the reactants, and the products. The 2 of N2 and the 2 of H2 have to stay, just like the N and the H have to be in the proportion 1 to 3 in this ratio. And in order to do this, the only way to do this is to multiply atoms and molecules on each side of the reaction arrow by positive whole numbers in order to get those substances to balance. So we steal a word from our math friends, the word coefficient. A coefficient is a number out in front of a variable. Our variables are not x, y, or z, but they are atoms or molecules or diatomic molecules. So what I'm going to do is I'm going to quick steal this chemical reaction and I'm going to drag it down a little bit so that I can leave myself some room, because we're going to talk about the process of balancing these chemical reactions. So let me see if I can get this right on the line. Let's talk about how to balance. Well, balancing is an inexact science. There is no one way to balance all chemical reactions. Each reaction balances a little bit differently. And so the ultimate goal is to just get the same number of atoms on each side. Now there's a couple of things that I would recommend you try, and these are my tips for success. They're not rules or requirements, but they are tips. And so the first tip I recommend everybody when they're developing this skill is first create the atom inventory. And what I mean by atom inventory is what I do is I make a count of which atoms and how many are on each side of the chemical reaction. So I have nitrogen and hydrogen on both sides, and on the left I have 2 nitrogens and 2 hydrogens, and on the right I have 1 nitrogen and 3 hydrogens. And so my first step is to take an official count of the atoms to start with. The next thing I do is I begin to balance, but I want to balance, and when I do so, I want to save the hydrogens and oxygens till last. And the reason I do this is because hydrogens and oxygens are oftentimes buggers when it comes to balancing. And if you just save them till the end, they just kind of work themselves out. And so this chemical reaction can be balanced starting with the nitrogens first. And I'm going to do that. I need to, as you can see, I have 1 nitrogen on the right and 2 on the left. So I'm going to double my nitrogen. So I'm going to multiply this whole side by 2. And when I multiply it by 2, I not only multiply the nitrogen by 2, but I also multiply the hydrogen by 2. So my 3 now becomes 6. And that's okay. You can multiply an entire molecule, basically changing both atoms. Now I go back to the other side, and I go, all right, well, 2 goes into 6 3 times. That's pretty easy. So I go up here and I multiply this by 3. 3 times 2 makes 6. And now I have balanced numbers on the bottom or underneath, and then I can safely assume that my numbers over the top are correct. Now I'm going to go ahead and erase these parentheses here on the NH3 because you don't really need them, but I put them in there to kind of help out. The other thing I might add is anytime there's a blank in front of a number, I might put a number 1. Now it's the same as if you don't put a number at all. A blank is the same as a number 1, but just for good practice, to make sure I have numbers in front of all my molecules and all my atoms and all my diatomics, I put a 1 in there. Now this is an example of an easy balancing problem, and I shared with you my first 2 little tips for success. Now I'm going to take you through a couple more examples on the next page, and I'm going to introduce to you a couple more tips for success to help you work these a little bit faster. Go through a couple more examples for you and actually share with you a couple more tips that I would suggest you try when you're working out some of the more difficult problems. Here's an example of one. It's not really all that difficult, but I'll still model for you how to do the atom inventory and such. So I start by splitting the reaction in two, and I write out my atoms on each side. I've got hydrogen and oxygen on both the left and right. And I start with 2 hydrogens and 2 oxygens on the left, 2 hydrogens and 1 oxygen on the right. Now, if you remember my last one, save oxygens to last. Well, you really don't have any option in this point because oxygen is the only one that's not balanced currently. So what you want to do is you double the oxygen by putting a 2 out in front, and that doubles the oxygen and also doubles the hydrogen. So now you have 4 hydrogens and 2 oxygens. So now you go back over to the left side, and you got to take care of the 2 hydrogens. 2 hydrogens versus 4 hydrogens, so 2 goes into 4 2 times, so multiply this by 2 to make this a 4. And now you've got 4 hydrogens on each side, 2 oxygens on each side. So my coefficients are 2, 1, and 2. So now I scroll over here and take a look at this next one. This one's a little bit more difficult, but no, not really all that big of a deal. I start with lithium and oxygen on each side. Lithium and oxygen are my 2 atoms that are in the reactants and products. So I start with 2 lithium and 1 oxygen versus 1 lithium and 2 oxygen. Now I'm going to follow my rule or my guideline for keeping oxygen to last here. So I'm going to double my lithium right off the bat to turn that into a 2. Remember, doubling the lithium doesn't double the oxygen because these 2 elements are separated by a plus sign. And so it only doubles the one of the two products here. Now I got to go and double my oxygen. And in order to do this, I have to double this molecule. So that turns oxygen to 2 and lithium to 4. And then you think to yourself, well, man, I just wrote a 2 in here. Can I change this number? Well, absolutely you can change this number. There's nothing saying that once you write a number in that it is the number. That number is definitely likely to change. And so you just come in and you erase the 2. And I need to double that number that I already wrote in. So 2 times 2 is 4, which makes this now 4. And now I double check my count, 4 and 4, 2 and 2. So my final answer is 2, 4, and 1. So that takes care of those. Now let's step up the difficulty a little bit. Here, I'm going to put this one into view, zoom out a little bit so you can see the full reaction. So I'm going to drop this down, and what you see right away is that this has more atoms in it. We don't have just 2 atoms, we in fact have 4 different atoms: lithium, lead, nitrogen, and oxygen. But what I also see is that nitrogen and oxygen come in the form of the polyatomic ion nitrate. I got nitrate here and nitrate over here. And my third guideline for you is that if you ever see polyatomics, keep the polyatomic ions together when possible. What this allows for us to do is to actually treat the NO3 as one substance. And when I'm writing out my inventory underneath, all I need to do is write out lithium, lead, and NO3 together. And that is the same on both sides, lithium, lead, and NO3. So if I treat it as one thing, it actually simplifies things for us. Instead of treating this as 2 nitrogens and 6 oxygens, it's just 2 NO3s. So there's 1, 1, and 2 NO3s, and over here I have 1, 1, and 1. So I keep polyatomic ions together, and I'm going to double my nitrate on the right-hand side. So I'm going to double my nitrate, and that turns lithium into double as well, because it doubles this molecule, but not the lead. So then I go back to the left, and I need to double my lithium to make 2, and then I double check that everything is the same, and it is. So my final answer is 2, 1, 2, 1. So that's my third rule or third guideline. Keep polyatomic ions together when possible. Now over here, what looks like a polyatomic ion, NO3, is in fact not a polyatomic ion. It's not a polyatomic ion because it's not combined with a cation. NO3 with a cation would be nitrate. NO3 by itself is just nitrogen trioxide. So I just need to treat this one as a normal split up nitrogen oxygen. 1, 3. Over here I have nitrogen and oxygen. Now pay close attention or be careful here because I have oxygen as part of NO2 and oxygen part as of O2. So it's just kind of all together added up. There are 4 total oxygens. There are, once again, 2 here and 2 there, so you add them up to make 4. Now, this brings me to my 4th guideline, my 4th little thing that I would help you to do problems like this. And that 4th guideline is a little strange. It's just something I do. And my guideline is watch out for odd numbers. And what I mean by that is if I've got an odd number trying to go into an even number, that's never going to go in nicely. In fact, odd numbers don't divide into even numbers. Even numbers divide into even numbers, but odd numbers don't. And that's not necessarily true. Odd numbers will divide into even numbers, but it won't work out. So here's what you're going to do. If you come across a situation like this, what you want to do is just multiply your odd number by the first even number you can think of, and that is 2. Turn your odd numbers even, because 3 is never going to go into 4 nicely. So what I do is I just double that to make 6, but it also doubles my nitrogen. Watch out for odd numbers. Make the odd numbers even. Sometimes just try something and see if it works. In fact, you may seem like this got me further from the balance, but in fact, this got me closer to balancing. And here's what I mean. So now go back and do the nitrogens. 2 here, 1 over here. So let's do 2 nitrogens. And now count up my total oxygens. A lot of people think, oh, you doubled your oxygens, so now you have 8. Well, actually, pay close attention. 2 times these 2 is 4, plus 2 more makes 6, not 8. Once again, the 2 in front of the NO2 only doubles the oxygen in NO2, not all the oxygen. So 2 times 2 plus 2 is this total of 6. Oh, hey, check that out. If I save the oxygens till last, they just kind of work themselves out. And the final answer here is 2, 2, 1. So here's another example. Probably, it doesn't really have polyatomic ions. Let's take a look. So I dropped the vertical dotted line, calcium, aluminum, and chlorine, calcium, aluminum, and chlorine. And I count. I got 1 calcium, 1 aluminum, 3 chlorine, 1 calcium, 1 aluminum, and 2 chlorine. So I come into this problem again where I need to, make my odd number even. And let's do it. Let's get rid of my odd number by multiplying it by 2. So multiply that by 2 makes 6, but it also multiplies my aluminum, but not my calcium. 2 does not touch my calcium, only the aluminum and chlorine. So now over here, I balance my aluminum by multiplying by 2, so that's pretty easy. And now I need to multiply my chlorine by a number. 2 goes into 6 3 times, so that's pretty easy. 3 makes 6, but that also multiplies my calcium 3 times, so that makes that 3. Now finally, I need to finish up by balancing my calcium. 1 goes into 3 3 times, and so make that a 3. That turns into a 3. And now I've got my final answer of 3, 2, 3, 2. Now what's nice about me doing these problems here in a video is that if you didn't catch that, just go ahead and rewind it and watch it again. You can watch me work that problem out a little bit more slowly or watch me do it again. And so the last thing I'm going to do is scroll over to this last one. What I've got here is a plethora of polyatomic ions. In fact, I have 2 polyatomic ions in this problem. I've got SO4 and NH4. So when I write out my my atom inventory, I've got aluminum, sulfate, ammonium, and bromine. So on this side, I'm going to match them up the same directly across, and I'm going to start counting. So I've got 2 aluminums, 3 sulfates, 1 ammonium, NH4, there's 1 of them, and 1 bromine. Over here I have 1 aluminum, 1 sulfate, 2 ammoniums, and 3 bromines. Now with something like this, I don't know, just pick one and see what works. And so your guess is as good as mine. I'm going to start with the aluminum. I'm going to double the aluminum over here by turning this into a 2. That turns my bromines into 6. All right, so my aluminums are balanced. Now since I changed bromine down here, what I'm going to do is actually work on bromine back to this side. So 1 goes into 6 6 times. So I'm just going to multiply this whole side by 6. And it not only multiplies my bromine times 6, but it's going to multiply by ammoniums times 6. So now that my ammonium has been changed, I go back to the other side and work on the ammonium. So every time I do something on one side, I fix it on the other. Now I did ammonia, now I'm going to do ammonium again. So 2 goes into 6 3 times, so multiply this by 3 to make 6, and now that also happens to multiply my sulfate times 3, and now I double check the sulfate and work on the sulfate on the other side. And look at that, they're matched, they're already balanced. I don't even have to add anything to the sulfates on the reactant side. So 2 aluminums, 3 sulfates, 6 ammoniums, and 6 bromines. Everything's balanced. And then up above, I just add in my 1s where I see blanks. My final answer is 1, 6, 2, 3. Last guideline for you is actually one that applies to a specific type of reaction. And that guideline is watch out for combustion reactions. Combustion reactions tend to be the most difficult types of balancing problems, at least of the ones that I'm going to be presenting to you. And if you're asking yourself the question, man, these are going to be hard. Mr. Calmy says these are going to be hard. Are they going to be on the quiz? Well, you bet your bottom dollar they're going to be on the quiz. You'll have to do at least one of these on the quiz coming up here in the future. So pay close attention because these are a bit tricky. Now I'm going to start by doing the same thing I did on all my other ones. I'm going to start with an atom inventory, C, H, and O on each side. So far, things look just straightforward. So 2 carbons, 6 hydrogens, and 2 oxygens left, 1 carbon, 2 hydrogens, and 3 oxygens. And if you're having trouble adding up the oxygens, there's 2 as part of this oxygen and plus 1 as part of this water. So 2 plus 1 is where I got my 3. Now, save the oxygens and hydrogens till last, so I'm going to start with the carbon. I'm going to double my carbon to turn that to a 2, but now my oxygen count just went up. Pay close attention. 2 times 2 is 4, plus 1 is 5. So oxygen didn't double, it actually went up only a little bit. It went up by 2 because I doubled only some of my oxygens, not all the oxygens. Now I'm going to tackle these hydrogens. And 2 goes into 6 nicely 3 times. So I'm going to put a 3 here. Oh, just kidding. I'm going to put a 3 over here to make this 6. And now I'm also going to readjust my oxygen count. So count them again. 2 times 2 is 4 plus 3 times 1. And 4 plus 3 is now 7. Now taking a step back, what type of reaction am I looking at? Well, it's a combustion reaction. If you remember back in the previous chapter 5, combustion reactions are always reactions that have a fuel plus oxygen give you carbon dioxide and water. So you'll know you're looking at a combustion reaction right off the bat because you'll see that it looks a lot like this with carbon dioxide and water as products and O2 as one of the reactants. And you're at this point of the balancing problem where you're trying to put 2 into 7, and 2 doesn't go into 7 evenly. 2 goes into 7 only a little bit, half of a molecule. 2 goes into 7 3.5 times. 2 times 3 is 6. 2 times 4 is 8. 2 times 3.5 is 7. And so we're going to do something, but then we're going to fix it. Something we can't do, but then we're actually going to do it, so just pay close attention. So 2 goes into 7 3.5 times. So I'm going to put a 3.5 right here as part of my O2 to turn this to 7. But you may think you're finished, but you can't have half a molecule. You just can't. And so in order to get rid of that half, what I'm going to do is actually do my last step. When you balance all the elements and everything looks good down here, what you then do is your last step is double everything in the problem. Double all your coefficients. So take 2 times 1 to make 2, and 2 times 3.5 to make 7, and 2 times 2 to make 4, and 2 times 3 to make 6. So my final answers, if I erase all the parts underneath, is 2, 7, 4, and 6. Now that little trick only works for combustion reactions. Just to review, I worked my way carbons and hydrogens first, and then I got to the oxygen, and I put in a half a molecule here. 2 goes into an odd number an uneven amount of times, and so I use a half molecule. So for a temporary point of the time, I write in a half a molecule, and then I go back and double all my coefficients to make numbers that aren't halves. So 2, 7, 4, 6. So that's one little trick you can do to handle combustion reactions. And you'll have to do one of these, and that's my recommendation for how to handle it. Well, that takes care of this video lesson on balancing chemical reactions. From here on out, it's just practice, practice, practice. Thanks for listening.